some. Okay. You want to remove this? Okay. First, about some preliminaries on graph and message passing neural networks, just to introduce the notation that you're going to use. Then we're going to describe a bit like the concept of expressivity, and then how to get this expressivity, which will lead to more powerful representations that are based on subgraphs. And then we will delve into what actually interests us, which is how to get this subgraph selection to be efficient. So to return as many subgraph as it is absolutely necessary without redundancies. And then we are going to describe some future directions and conclude the talk. So the main references for this talk are these two. The first, equivalent subgraph aggregation networks, which was a joint work that actually started this subgraph that I've been working on. And then the second one, which is mainly the topic of this talk, that is how to get this selection to be efficient. So I will start with these preliminaries. So we will denote a graph as a tuple, V, E, and X. V will be the set of nodes, E the set of edges, and X the node attributes. And we will denote by N the finality of this set of edges. Maybe some important part is how we will describe this adjacency matrix, which, for example, you can see here for this very simple graph that is on the left. And in this particular example, we have that in dark gray, we have the connectivity. So we denote by dark gray whether two nodes are adjacent to each other. And by this, instead, light gray whether they aren't adjacent. So the most widely used GNNs are arguably the message passing neural networks, which proceed by updating the representation of nodes at each layer. So the representation of node B at a certain layer K is obtained by using a message function, which takes as input the representation of all the neighbors of node B at the previous layer. And then we update the representation of node B to get the representation indeed at this layer K+1 by means of an update function that will take the representation of B at the previous layer and then this message that we have just computed. Then we can get the graph representation by simply employing a readout function that will take the multi-set of node representations, for example, at the last layer L. So in this way, we obtain the invariance to permutation of the node IDs, and therefore we can ensure that isomorphic graphs will get the same representation, which is a desiderata that, of course, we are happy to actually meet. However, despite the large applicability of this message passing neural network, they still have a major limitation, which is the bounded expressive power. In particular, this means that no matter how we parameterize the message and update functions, the message passing neural network have a bounded expressive power, which means that there exist non-isomorphic graphs that cannot be distinguished by message passing neural networks. And the two here are a very, very simple example where you can clearly see that these two graphs are not isomorphic because we cannot map one to the other. But it's also true that this message passing neural network cannot actually distinguish them. And this is due to their expressivity limit, which is the same one as the WL test or WL heuristic, which is a necessary but insufficient condition for graph isomorphism. It works very simply and in a way that you can clearly see that it's very similar to the message passing neural network. We have that the node B updates its color at layer k+1 by using an hash function that takes the color of node B at the previous layer and the multi-set of colors of its neighbors at the previous layer as well. So as an example, you can again consider these very two simple graphs. And then we start by applying this iterative update. You can see that the light blue nodes become light blue because they take as input this like one gray that is their representation of the previous layer, and then this multi-set of 3 elements because they have 3 neighbors which were gray at the previous layer, and therefore like we denote this the output of this hash function applied to these inputs as light blue. For the yellow one, it's very similar, but you can see the difference is in the fact that the number of neighbors for the yellow, well, it's orange, sorry, not yellow. For the orange one is 2 the number of neighbors instead of 3. So it's simply another color that we denote as orange. Then we repeat, and we can get these new colors that are green and purple. And since this one is a refinement of the previous color, which means that the nodes are like the set of nodes that have the same color still maintain the same color in this new update. We finish and we collect these colors in an histogram that maintains how many nodes have a specific color. So for these 2 graphs, you can see that at the end, 4 nodes have purple color and 2 nodes have green color. So these 2 graphs have the same representation, which is this histogram, and therefore are deemed possibly isomorphic, although we know that they are clearly not isomorphic. So due to this expressivity bound, message passing neural network cannot distinguish some non-isomorphic graphs. For example, the 2 that we have seen, but there are many other exemplary graphs, and therefore they will fail if the target is different for those indistinguishable graphs. But I think, like, more importantly, they cannot induce count substructures of 3 or more nodes. So for example, they cannot count the number of triangles. And this is certainly clear because in the previous 2 graphs, one had 2 triangles and another didn't have any triangles. So if they had this ability of counting, they would disambiguate those. So there has been like some literature into kind of asking how can we go beyond this expressivity limit, and to like all this literature have tried to focus on what does it actually mean to go beyond some expressivity limit. And since there is some, so we know that message passing neural network are bounded by the WL test, and the WL test has higher order counterparts, which have increasing expressivity. Then many methods have tried to kind of map the expressive power of this new architecture to the one of the of these higher order counterparts of WL. So the idea is then becomes, can we design architectures that are as expressive as KWL for some K that we decide and it's based on some task that we are interested in. Ideally, it would be like, can we design architectures that are as expressive as KWL for like the highest K that we can think of. So subgraph GNNs, we are going to see are one way of getting this increased expressive power. The intuition behind these subgraph GNNs is that WL equivalent graphs, such as the 2 that we have just seen, may contain subgraphs that are instead WL distinguishable. So if we consider here some node deleted subgraphs that are obtained from the original graph simply by deleting one node, then we can apply the WL test on these node deleted subgraphs, and we can see that this subgraph gets different histograms, and therefore we can say that they are non-isomorphic. So it's easy to see that there exist certain cases where we just need to create these subgraphs to then understand that the original graphs are non-isomorphic. So In particular, if we consider these two original graphs that we started on, then we can construct the bag of subgraphs, each subgraph obtained in this case by deleting one node. Then we can apply the WL test on each subgraph separately, for example. We can collect all the histograms into a set. And then we can see that the set of histograms is different, and therefore we can disambiguate these two original graphs. So this is exactly the idea of subgraph GNNs. So, of course, this was with WL tests, while subgraph GNN are still neural networks. So we want to learn the graph representations. So how to do so? We first need to treat the graph as a bag of subgraphs with what we call a subgraph generation policy. And ideally, for isomorphic graphs, the bag must be the same so that we can still recognize that we started from the same graph, because it was also a property that the message passing neural networks had. And then we can employ an architecture that processes the bags of subgraphs. So exactly in this way, we first need to generate the subgraph, and then we need to pass it to some neural encoder. Of course, like to design this neural encoder, we need to understand what is the symmetry group of the object that we have. We have the bag of the subgraphs, right? So to understand the symmetry group, we can stack the adjacency matrices of the subgraphs, one on top of the other. So you can see here that this cube, for example, is like each row of the cube is one of the adjacency matrices of the subgraphs, and we just stack them one on top of the other. Then we need to note that the order of the subgraphs in the bag is irrelevant, because it's still a bag or a set, a multi-set of subgraphs, but also the order of the nodes in a subgraph is irrelevant as it is for the original graph. Therefore, we can then conclude that the architecture must be equivariant to SM times, to the direct product of SM and SM, where SM is responsible of permuting the subgraphs in the bag, and SM permutes the nodes in the subgraphs. And it's the same permutation for all the subgraphs in the bag. This led to the architecture that we designed, that was this, what we call DSS GNN, which, exactly as we said, first generate the subgraphs according to some deterministic policy. And then the neural encoder was specified in this way, where we passed each subgraph to an MPNN, and we also passed the aggregation of the subgraphs to an additional MPNN, and then we summed the corresponding representation to obtain a new representation for each subgraph. And this architecture was inspired by the DSS GNN that exists in the literature. And it's equivalent to SM times SM. An additional variant that we considered was something that is even simpler, and it simply applies an MPNN on each subgraph separately. Of course, like this, just maybe I didn't say it before, but this MPNN is the same for all the subgraphs. It's just that it is applied to each of them as if they were separate, to obtain a new representation for each subgraph. And this is a variant to SM, like to the red product of SM and SM, because the nodes can permute independently in each subgraph, since there isn't that additional component. This layer idea was actually studied in many concurrent work, including one from Professor Pandit. So what do we gain from this? I think the important part is that there exist subgraph selection policies such that either DS-GNN or DSS-GNN, so these two-layer variants, are strictly more expressive than message passing neural network, which was our original objective. And the above is also true for other variants of subgraph GNNs. Indeed, like there are many possible variations of subgraph GNNs layers, and there are many other operations that can be included. For example, a simple operation is the one that, so a node in a subgraph can include the representation of the subgraph that was generated by it. So that was generated, for example, by deleting that node. And this was studied in also some work that was concurrent. But regardless of the layer design, subgraph GNNs are hampered by the cost associated with performing the message passing on all the subgraphs. And this actually leads to the core of this talk. So how can we get efficient subgraph GNNs? Ideally, we wouldn't want to perform message passing in all the subgraphs because they can be potentially many. We focused on node-based policies where each subgraph is tied to a specific node, which is denoted as the root node of that subgraph. For example, the first node generates the first subgraph. So suppose this is our graph. Then by this node marking generation policy, we generate as many subgraphs as the number of nodes. And each subgraph is simply obtained by marking one node in the original graph. There are also many other node-based policies. For example, node deletion, that is one that we saw. Egonets, or marked egonets, where each node generates a subgraph by simply getting the ego network around it. In these node-based generation policies, there are as many subgraphs in the bag as there are nodes in the graph. And therefore, the complexity is n squared times d compared to n times d of an NPNN, with d the maximum node degree. So we actually, like, just by considering subgraph, we need to perform this message passing on each of the subgraphs, and therefore we actually lose one n. So the question becomes, is it really necessary to consider all the subgraphs in the bank? And the answer is not necessarily. So we saw, for example, this example before, and we even though we started from these WL indistinguishable graphs, if we generate the bags, each containing one subgraph, we could already distinguish these two, because even just one subgraph can already tell us these are non-isomorphic. And this is not the only case. So for example, we can consider CSL graphs. And even though these CSL graphs are a family of non-isomorphic but WL indistinguishable graphs, once we generate the bag containing one subgraph obtained by marking one node, we can already deem them non-isomorphic because the histograms are different. However, these cases are like too simplistic because random selection is sufficient, especially in the case that I'm showing here, because all the nodes are symmetric. So just randomly selecting one node to mark, it's sufficient. So let's define a bit more complicated, a family of graphs that is a bit more complicated, but still like very interesting and still based on what we just saw. So we defined an NL-CSL graph as the graph obtained by L disconnected non-isomorphic CSL graphs, each with n nodes. So this one is one example. It's just one NL-CSL graph. And you can see that there are many disconnected components, many actually L, and each of them has n nodes. Obviously, they are like all the non-isomorphic NL-CSL graphs that have the same N and L are WL indistinguishable because each of their component is indistinguishable. And also using all L times N subgraphs, where each subgraph is obtained by marking one node, will allow us to identify their isomorphism type. So, but then the question becomes, do we need all these subgraphs again? And the answer is actually no. Because, for example, if we consider a node marking based policy, it is necessary and sufficient to mark only one node in each CSL subgraph. So in this figure, we can see that there are, like we show, of course, there are many dots that include like other parts that are not visible, but each subgraph is obtained by marking exactly one node. And what we want to do is mark one node per connected component, so per CSL subgraph. So since there are L connected components, we need only L subgraphs. And they need to be carefully selected because not L subgraph randomly chosen. They need to be one in each CSL subgraph, like in each connected component. And of course, L is smaller than L times N. That is the possible number of subgraphs that I could generate from here. So what about random selection? And we actually showed that the probability that a random selection of L subgraphs can identify the isomorphism type of an NL CSL graph is L factorial divided by L to the power of L, which goes to 0. So this means that the expected number of random selections before identification is L log n d of L. So this is because randomly selecting subgraphs means that we might consider multiple subgraphs that all mark nodes in the same CSL subgraph. Exactly what I'm showing here, because, for example, the subgraph on the right is completely unnecessary, because in the subgraph on the left, we already marked one node in that connected component. So we could already identify the isomorphism time for that connected component. What we're missing is the other connected component. And just by random selection, I have so many possibilities, I'm not guaranteed to get the other connected component. So this leads to our method that we call policy learn. So how can we learn these efficient selection policies? We start by a bag that contains only the original graph. Then we feed the bag into the selection network, which outputs a distribution over the nodes. Then we sample a node and add the subgraph that it is root of to the bag. So exactly like this sampling is based on this probability distribution that is given by a selection network, given the current bag that we have. And we repeat this t times until we have collected the t subgraphs plus the original graph that we had at the beginning. And this will form the bag, instead of considering all the possible subgraphs that we could have generated. Once we are happy with our selection, we can go and pass the bag to the prediction network for the downstream task. And this is done all end-to-end. So just a note, a naive sampling is non-differentiable. So to backpropagate to the sampling strategy, we use the well-known Gamble softmax trick, which we use directly as marking. And I think I was discussing with Houghton before that what is interesting here is sort of like learning the labeling trick, because the marking is actually exactly where the gradient flows back. And it is what we never materialize the subgraphs, we directly materialize the marking that will then define the subgraph that you're going to add to the bag. Also, importantly, both the selection network and the prediction networks are subgraph GNNs, because they both take bags of subgraphs. And if we recall these NL CSL graphs, then we can actually easily show that policy learn with T equal L can identify the isomorphism type of these NL CSL graphs. How? It's very simple. Like the selection network can always distinguish the nodes belonging to the CSL subgraphs that have already been marked, and therefore can assign them a 0 probability of being sampled. So suppose that this is our bag, this one on the left. We have already marked that node on the left subgraph, on the left CSL subgraph, so on the left connected component. Then our selection network can already identify all the nodes there and assign them a 0 probability, while the remaining ones will have uniform probability of being sampled, and they are in red. And therefore, our sampling procedure will only sample from those we care about. We'll never sample from the ones we have assigned a 0 probability. And then we can add this new subgraph to the bag. So similarly to our work, there is like the recently proposed OSAN learns the selection policy rather than instead employing the full bag. And there are several differences, including the practical differences in the method, which is like in OSAN, the bag is generated in one shot instead of this sequential process. And since it is generated in one shot, the selection network is also an MPNN. So you can see here that we take the original graph, we feed it to the selection network, and then obtain the bag that we are interested in and pass through the prediction network. But what is the difference? So consider the case here of these NL CSL graphs. Once we feed it to the selection network, all the nodes are completely indistinguishable by design. Then once we go and sample, we still behave as uniform random sampling. So we might still end up sampling nodes in the same connected component as it can be seen here. And indeed, the OSAN actually behaves exactly like random in these cases. And the probability that OSAN with T equal L can identify the isomorphism type of an NL CSL graph is indeed the same as the random sampling L factorial divided by L to the power of L. So we discussed about, like I tried to convince you that this was more efficient, but actually how more efficient, what does this even mean? So we said that the selection network performs T iterations. At each iteration, we add a new subgraph. And how do we do so? By selecting the subgraph, just by passing the last subgraph that was added through an MPNN. So we just need to process one new subgraph at each iteration, because the previous one can still use their subgraph representation, which means that the overall time complexity is T times N times D, compared to this N squared times D of the full bag subgraph GNNs, where D is the maximum node degree again. So in our experiments, we actually used T equal 2 or 5, which is like very small and also constant. And it is really an improvement with respect to these full bag subgraph GNNs. So, for example, on the zinc dataset, PolicyLearn significantly improves over OSAN and surpasses the random baseline. So you can see that, first of all, compared to the full bag, what we call full, the training time is halved. The test time is also reduced, and of course, like we lose into the MIE, but it's a trade-off as usual. There is also in the paper, there is also the result with T equal 5, where the MIE is better, like including more subgraph is gonna get better performances, but of course at the expenses of the training time. With respect to OSAN, with the same number of subgraphs, we get an improvement that is significant, and this is due to the design choices that we made on this sequential path. And also with respect to random, we can get better performances at the expenses of little training and test time increases. So more importantly, we can actually allow the applicability of subgraph GNNs to graphs that are larger. For example, those in the Reddit binary dataset, where there are right, there are like 430 nodes, which is not even large, but subgraph GNN, of course, generating the 430 subgraphs cannot run. So they go directly out of memory on like 40 gigabytes GPU. So to conclude, we saw that decomposing the graphs into bag of subgraphs breaks the expressivity limit of message passing neural networks. And we discussed that we can carefully select a number of subgraphs instead of using the full bag to get the same expressive power in certain cases, of course. So what's next? We already did some preliminary work where we combined subgraph GNNs and graph transformers, because you can imagine that instead of considering the original graph, you can consider this bag of subgraphs and then use a positional encoding that is tailored for this new graph that you are considering. And then, like, also what's next? Like, a question would be, is there something even more practical? Because I don't know if you know, but the generation policy was always the same. Like, we changed the selection policy. So we changed which subgraph to use, but how to generate the subgraph, which was, for example, by marking one node in the original graph, was always the same. While in reality, we could change that. What if we use not really subgraphs in the traditional sense? What if we actually considered some sort of like clustering of the nodes as the subgraph that so some sort of like higher order structure. And this is like a work in progress that we are doing, but like there's still so much to do. And of course, like I'm open to any question and we can discuss together. So thank you.
Thank you, Beatrice. It's nice. So I just have a few quick questions.
Of course, of course.
Like the first question was like, I was wondering, did you use the like cross entropy loss directly to train the neural network end to end? Because why I ask this question, because in my opinion, I feel like your method is kind of similar to one of my previous work in some sense, but we have a different starting point. We kind of starting from generating interpretable subgraph to kind of, we derive a mechanism, architecture from information bottleneck. And we, in some sense, we also employ the Gumbel-Soft max trick. We kind of assign each node a binary attention to select a subgraph for the prediction task, for downstream prediction task. And so when we train our method, we kind of use cross entropy loss and information bottleneck loss, or regularizer derived from the information bottleneck. So I was just wondering, did you directly use the cross entropy loss to supervise your selection policy? And do you consider like supervise your policy network like in a better way?
So that's a very nice question. Thank you. So we only use the cross entropy. What we did, it's in the paper, we have a comparison on whether the selector is allowed to select the same subgraph, or if it's not allowed to select the same subgraph. But in principle, if you let it train, it actually understands that it shouldn't select the same subgraph because it's not beneficial for the downstream task. So I think this is a comparison that we have in the appendix, but in the end, in the experiment that are in the main paper, we actually didn't constrain it to select the same, to avoid selecting the same subgraph. Regarding, in principle, it could be that there are still overlapping subgraphs, like nodes that are marked that are very, very close to each other. But still, in practice, we never saw it to be a problem because it's still not beneficial for the downstream task. So it tends to learn the subgraph that are distant and not overlapping in order then to have this marking that can be seen everywhere in the graph, in the original graph. So we didn't use any additional regularization.
Got it.
I think, so in OSAN, they had something a bit different because since they sample at all together, all at the same time, they have an additional regularizer that penalizes the overlapping. But for us, since the procedure is also sequential, you see already what you have selected. So you shouldn't then you should learn to give to the nodes that are reachable from what you have selected a very low probability.
Got it. Thanks. And I have another question. It's have you ever tried to evaluate your method on different or other tasks for molecules? I've seen you have some results on zinc. The reason why I asked this question is one of my previous work. It's also in some sense subgraph based method. We just find this kind of method, but in our paper we didn't prove its expressive power. But I feel like your method kind of can inspire us a way to prove the expressibility of my method. So, but I just want to say empirically, I find my method can work pretty well on molecular-based method. So I was just wondering, do you also observe the same thing?
Yeah, it's true, but I think so. It's also true that these subgraph methods are still kind of limited. This is a step in the direction of getting them to be more efficient, but it's still they're still very much burden in the complexity. So the benchmark that we tested were small, like this zinc. Also the Reddit is social network, it's not molecules, but still cannot be considered large. So in the sense that there is still so much to then really improve before actually saying how it performs on this, because I can tell you, yes, on social network performs well, but actually we have tested only on Reddit, and it's not even that big. So I'm not sure it would be a valid sentence, So I think it's true that it performs very well on molecules. Regarding the other method, the other benchmarks, I'm not sure how it performs because we haven't really evaluated that much on the other benchmarks, since there aren't many that are still doable for this subgraph GNNs. On Reddit, that is a smallish social network, it performed well. Maybe it would be interesting to see on other social network datasets.
Yeah, thanks. Yeah, because I was just thinking in molecules we have a lot of carbon rings that needs expressive power. So perhaps in those data sets you can see the greatest improvements. Yeah.
I completely agree. Maybe just that on social networks there are, for example, triangles that might be important as well, and those are also not captured by the message passing neural network. So potentially there is something there as well for those triangles. So the improvement might be due to the triangle counts.
Yeah, that makes sense. Thanks.
No problem, thank you.
So
Hi, Beatrice. Oh,
yeah, Eli,
sorry.
there's a one comment regarding CG. So Beatrice, so will the zinc data set is a molecule one, right?
Yes, yes, it is.
Yeah, I'm not sure why. Yeah, so CG, you are asking for the other molecular data set.
Yeah,
For example, some
like
OGV,
yeah,
OGB
Oh,
ones.
yeah, there are results.
Okay.
Yeah, sorry, I didn't put them here, but in the paper we tested on the OGP G, yeah, all the graph classification. So the mole HIB, mole base.
HIV, their lab base, and the LTF 21.
Yeah,
Yes, it's over here. It's in table 3 of the paper.
and we also
Got it.
tested in the appendix.
Yeah, got it. Thanks.
Yeah, so hi, Beatrice. So this is Eli, and I might miss something, but I have a confusion about like the comparison with your method with Olsen.
Yeah,
Like,
of course.
yeah, so so first of all, does your method and Olsen both train in an end-to-end fashion, right?
Yes.
Okay, so and then you just mentioned the reason why Olsen might not perform well is because in their selection net, due to the symmetry, they will act like the uniform random sampling. Is that?
Yes, it can end up into uniform random sampling. Yes.
Yes, but I wonder but since we are trained in an end-to-end fashion, so we also have a back propagation, which means the loss can also affect through back propagation to affect the selection network. So in that case, the selection net in Olsen will probably act not like purely random sampling.
So the problem is that the selection network is an MPNN. So you really cannot distinguish those connected components, and you cannot distinguish the nodes in each of these connected components. So they are like indistinguishable by design. So there is no loss that can help you in the back propagation. Like you will get a bad loss because you will get whatever sampling you're gonna end up having, which might not be the optimal one that you would like. But then once you go in the backward, you go change your parameters of the selection network, but still they're gonna give you exactly the same output for every node. That's what is bad for the sampling, because necessarily all the nodes in all these subgraph like connected components they are completely symmetric from the standpoint of the selection network. So they need to receive exactly the same information, like to output the same information.
I see. So you mean that no matter what ways in this selection net, they will output the same probability assignment for all nodes?
Exactly, because it's so in this simplistic case, these connected components are like separated, right? So they are like really nice components. And then we know that these, for example, these two graphs here, these and these are completely WL equivalent. So and of course each node in each of them is symmetric to the other, because there is no difference. So they are going to receive exactly the same output from the selection network regardless of the weight. So even if like this procedure is gonna change the weights, you're gonna output this.
I see. Okay, thank you.
Of course, this is a pathological example. I don't want to say that it's not, but it's a case where since you are using a selection network and NPNN and you don't do these iterative updates, then you cannot do better than random.
Yeah, thank you.
Sorry, I also have a quick question to see if my understanding is correct. So when you do the sampling of the subgraph, so although like I know that like the probability distribution is kind of permutation equivalence, but actually when you do like after the sampling, so that your prediction is no longer permutation equivalent, right?
It's true. It depends on what exactly. It's true. It's true. There is this sampling component that kind of. So it's like equivalent in expectation.
Okay. Then like I wonder like in practice, will that just kind of will kind of lead to like the prediction will have high variance or something. Like for the same graph, sometimes we'll predict like complete different due to this. Will this happen?
So it's true while training, but it converts like at the end is very confident in the prediction. So like at the end, the probability distribution is not uniform at all. It's actually very high for certain nodes, potentially also only one, depending on the symmetries, and very low for the others. So there isn't this much of this variability.
I see.
During training, for sure, especially at the very beginning.
I see. Got it. Thank you.
No problem.
So I actually have a question. So Beatrice, I will so your method is using an iterative method to avoid the issue of this OSAN. So may I understand that can you quickly like go over that iterative process again? So I just would like to know how you break this.
Yeah, of course. So for example, here in this example, we start by only the original graph, but like imagine that the bag is at this point it contains two subgraphs that are the two shown here. One is the original graph because we started just by the original graph, and the other one is obtained by marking this node in gray here.
So here I have a question: how you mark this node?
Yeah,
this is from the previous iteration.
Yes,
yeah.
It's from the previous iteration.
Oh, okay. Now, then from the previous iteration, then what's the starting point? The starting point will be everything will be the same, or just the original graph, just the original, for example.
Yes, at the beginning we start just with the original graph, which means that in this case, of course, the probability distribution is uniform over all the nodes when we have only the original graph because nothing is marked. And then we sample one node.
I see. In this case, in the first iteration, in this case, it will be uniform, right? For every node, for both of the graph will be uniform. And then you sample one of it. Essentially, we are using randomness to break the symmetry. Kind of, right? And then from the second step, because we have already break the symmetry, then the second step, it just will enhance the procedure to break the symmetry, kind of.
Yeah,
right? So,
we have broken the first symmetries. We know that, for example, in this part we like the selection network can assign here 0 probability of being sampled because it's already in the input the marking of this subcomponent. Or only to the other can assign the uniform probability, and then we're going to sample uniformly from the rest. So here, for example, this node.
I see. So, okay, essentially you are trying to inject the randomness during the message passing procedure to break the symmetry, but also just still the message passing procedure is deterministic. The randomness is just generated in the very end, but you are kind of inject the randomness during the message passing, kind of. I have to say.
Because we often inject the randomness when sampling, but the distribution doesn't care of any, like the distribution that they have. Yeah, for example, here, up until sampling, there is no randomness.
So regarding this, I'm thinking, even do we really need to sample subgraph here, or do we really need to sample node and label that node here? For example, you can do this. You can do one round message passing, and then use the node feature there to generate probability, and then sample and then run Gumbel softmax, right? And then the Gumbel softmax is just let's say a new attribute for that node, for example, and then I run another round of message passing. So I was wondering that way can also do the task.
It is exactly like this. Maybe like I'm describing it in a way that seems more complicated, but it is exactly like this. What we do is
okay.
the labeling and then add it to the original graph. There is no subgraph construction. It's just
I
like
see.
the labeling.
I see. Okay, let me think what's I see. So I was wondering, for this, have you tried to see whether the benefit indeed comes from the expressive power or not? For example, the training loss, because I also have another guess. So I guess the ultimate benefit result, like the benefit you get, is not only from expressive power, but maybe also from generalization. Because just as Siqi mentioned, like when you inject the randomness during the procedure, you actually make the model more robust to the noise perturbation, and kind of you make your model more distribution nolly robust.
In reality, this sampling, it's like with the Gumbel softmax, it's one opt in the forward, but the backward still considers the probabilities. So it's true that it's more robust, but in reality, the network in the forward pass only sees like 0 and 1 that actually means the marked, it's 1 and the not marked.
Yeah. I understand it's have like a 0-1 thing. So, but I'm just a guess. So because when you just check the testing data performance, so I guess it mixes two things. One is like expressive power. The other part is the generalization. So my feeling is maybe this method is not only, of course, definitely it's good for expressive power, because essentially we inject the randomness here to break symmetry, right? So essentially this is why it has better expressive power. But I also guess this is also good for generalization, because we in some sense perturb the original graph to some extent, and make your model more robust to that. But this is just my guess. So if you don't agree, it's fine. So I'm just curious. So whether you have got a chance to check the training loss also. Yeah.
So it's true that it's also better for generalization, because the training loss is a bit worse than when using all the subgraphs, and it can be so. While the test ones are most of the time very similar, so the gap range generalization, it's true that like it tends to overfit less. Especially because we keep changing the subgraphs, and there is this marking that keeps changing. So I completely agree. I think like understanding exactly the generalization capabilities would be very interesting. And
so what I suggest, you may check Siqi's work a little bit. So Siqi, maybe later you can send Beatrice the link to the paper or something. Yeah, so you can read through that, like, because that paper, we almost, as Siqi mentioned, like we almost use the same technique, but that one is more for the generalization side. We didn't try like a
Yeah, please send it.
Yeah. So you can check about that work. Yeah. So I guess is yeah. So you can definitely check that work, I guess. Any other questions I have? I don't think on my side is fine. So yeah, so just one thing. Have you tried to so you I think you show some training time, right? So I was wondering I think regarding training, I have two questions. So one is, have you seen any convergence issue regarding this? So you just need to double the training complexity of GIN. So this is a little bit shock to me, because I guess I'm not sure whether this will just take a much longer time. Yeah, but you find like just even less than double, I think maybe less than 2 times training time of GIN, the model has already converged.
Right, because here we are just studying one subgraph, right? Like t = 2 means we from the original graph, we add one subgraph and then we pass it to the.
Yeah. And the terminology is thing. So, but here you are saying subgraph essentially, but let's say in practice you didn't extract subgraph. So here you mentioned 2 subgraph essentially correspond to you inject randomness twice,
Yeah,
right?
it's
Yeah.
true. Like the terminology subgraph is maybe not very good. Like it's what it's called in these papers because.
I understand. In this context, yes, you can call it a subgraph. But my impression is more like inject randomness for how many iterations. Yeah. So okay.
That's really true. And
Yeah.
so yeah, there is no extraction of subgraphs. It's just like this concatenation of the labeling of the marking.
Yeah. Oh. Okay. Yeah, okay. And then I think that's fine. So because my only concern is just the training time, but it seems that the training time here is fine. And when you do the testing, are you still do like a 0-1 marking, or you just use soft value in testing case?
Which are the right? No, yeah, you use a 0-1 exactly as in train.
I see. Then okay, interesting. Then the randomness there is not huge, because if you use 0-1, my feeling is you will have a lot of variance, a large variance here, but it seems also okay, also fine. Okay, it's fine. Yeah.
Yeah, you might have large variance at the very early stage of the training, but then it really sort of like the probability distribution is very far from uniform at the end of the training. So if the model is very confident on the selection, it becomes very confident on the selection. So, or more or less, it becomes very confident on the probability distribution and how it should look like. And therefore, then the sampling is more or less always the same, because there is like one node that has way larger probability of getting sampled than the others, one or a few.
Okay, good. So I have no other questions. Thank you so much. Yeah.
Thank you for asking.
Okay, so I have one last question is that I know that for random sampling, we don't know, it not necessarily be more powerful than the fallback of subgraph or the other case. So whether we know clearly about the hierarchy between the policy learned subgraph, for subgraph, and the randomness in that case, do we know their hierarchies in regarding to the expressness?
So yeah, like it depends, because it's always like what we could prove is that we can parameterize random distribution. So like there exist ways for which the policy learner can implement random. So I think you can say that then it means that policy learning is a bit more expressive, but it's not very proper terminology, right? And then there are like, we could also prove the same for awesome. So we can parameterize all the probability distribution that awesome can parameterize. And what we could prove is that we are still below 4WL, because there are the strongly regular graphs of the same parameters that we cannot distinguish. But this is it. Like we don't even, in principle, we don't even know whether policy learner has the same expressive power as the pullback or.
Also, I know, like in practice, the express power is not necessarily associated with the actual performance, because I read the table 3 and then I realized in some cases that policy learned the performance is below fallback of subgraph, but sometimes they exceeded the performance of fallback of subgraph. That's why I want to know whether we have something to interpret this phenomenon over here. Yeah.
That's very good. I think what we could how we explained it was more or less the fact that for those cases where policy learning was better than full bag, where those data sets that have generalizability problems, where actually the test set is a bit different than the training set, and therefore like sometimes overfitting over the training set and using the full bag doesn't necessarily generalize on tests that well. While maybe having this randomness even in the training part can help you then also for the test capabilities.
Got it. One last comment. Whether we have a principal way to select the number of the labeling, the T over there.
That's a good question. So, no, not necessarily. It's a hyperparameter that we can choose. We tried also adding a new node that was connected to everything that decided whether we should stop. But in reality, there is no reason for the model to stop, unless we had some regularization. Because in principle, the model can use all the subgraphs. There is nothing that.
But the T is the linearly with respect to the complexity of the model, right?
That's why, unless we had some regularization that kind of tries to tell the model to use the least, like the less T as, the smallest T as possible, then and we didn't have any regularization. In the end, then there is no reason to choose a small number of subgraphs, right? But yeah, I'm not sure. I think we actually saw that with T equal 5 already, we were very, very similar to the full bag. So, and 5 is such a smaller number. So I guess if 5 seems a reasonable number, I just use 5 or 8. I think in the paper we have experiments 5 up to 8. And those were really already reaching the complexity of the full bag. So there was no reason to go beyond that. So at least it's much smaller than the full bag. But I agree with you. I don't know, it's an hyperparameter, so maybe we can just test.
It also depends on the data set on the graph.
Of course.
Okay, got it. Thank you.
So maybe I have to leave because I have another meeting. So Beatrice, thank you so much for coming here and give us this talk. This is a very nice talk. Okay, so